edition of Office Hours today for Appearance Theory. Our speaker today will be Noah Morgan, our application specialist, who has a lot of great knowledge to share on this topic. If you're not familiar with Office Hours, it's 20 to 25 minutes of a presentation, and then we open the floor up to you for questions. If we don't get to your questions, we will contact you after the event to answer them. We are recording this presentation, so it will be loaded to our YouTube page. So you will get a link to that, and it will be available if you need to watch it at another time or would like to share it with your colleagues. The chat is open for questions, so please feel free to put your questions in there. And I'm going to do my best to not cough while trying to read those questions to Noah. That way we can get through this presentation. If you have any problems with the audio, I did put some phone information in there. It looks like one person may have had some problems, but they're good now. And I think I mentioned we were recording this, so I'm going to turn it over to Noah now.
Like Sherry said, today we'll be going over appearance theory. Specifically, we'll be getting into the wave scan, one of our appearance instruments, and what it measures, how it measures, and then what scales it uses, and just a full encompassing understanding of what that instrument does and why it's useful. So without further ado, let's get into it. What we'll be really focusing on, again, is appearance, but specifically the phenomenon of waviness, also known as orange peel, and brilliance, also known as DOI, or distinctness of image. And from these examples that you can see, you can kind of get a better understanding of what that actually is. You know, when we're talking about waviness or orange peel, it's really self-explanatory. It's when a surface appears to look like an orange, the surface of an orange, where it's very bumpy, lots of structure. And in some cases, if we're making a premium product, we don't want that structure to be similar to an orange peel. It's not a very pleasant image to look at. And then when we look at something like the brilliance or the DOI of that appearance, what we're looking at there is essentially how fuzzy is that reflected image. If you have something that's high-end premium piece of material, you want to see a good appearance on that being very sharp reflected images, and very smooth surfaces, very homogeneous, and we want to be able to control that. And so using the wave scan, you're able to quantify what these actual appearance metrics are and put values to what those appearances look like. So getting into why it has this appearance. Any type of surface, when you're looking at that surface, what you have is you have a light source that's hitting that surface, and whatever structure that's on that surface, in this case we see some small wave structures, we have that light being reflected back at different angles, which means not all of that light's going directly back to the observer in the situation. And what that creates is a wavy light or a dark pattern, because if you can imagine, some of that light's being reflected at some angles, and that can then cast shadows over some of the other structures, and therefore you have this wavy type pattern that you're seeing on that surface. And what we find is that these wavy patterns are dependent on how far we are from that surface. So for example, if we're 40 centimeters away, let's say that's about an arm's distance length away, when we're looking at that surface, because we're so close now, we can start to see these very small structures. Historically, they're called short waves. And we'll get into what those mean and what that means and how that was developed. But as we go further from that surface, let's say we're 3 meters away, what we're seeing now is these longer wave structures. Because we're not so close, we can't see every bit of the details. We can see that now everything starts to come together in a different type of pattern. And now those short waves become those longer waves. And a great example is this here. So when you're about 40 centimeters away or about arm's distance away from the surface, what you're seeing is, in this example, we have a bunch of just random letters that are scattered about in a random orientation. But as we get further from that surface and zoom out, we find that all of those small structures, or all of those letters that are just randomly scattered about that surface, is actually in the form of a larger pattern. And that's what we're seeing when we have these smaller structures at a close distance. But when we get further and further away, we start to see that they actually form these larger wave structures at a further distance away. And so using that idea there, you can understand why there were initially two scales that were created, one being the short wave for those close, smaller structures that you can see, and one being the long wave, the LW value for those structures that we see once we get further and further away. On this graph here is also something important to note. What you see here on the x-axis is wavelength, so the actual size of the structure. So if you're thinking about a surface here, and you physically measure the distance of those divots that you're seeing on that surface, then that would be essentially the structure size. And then on the y-axis, we just have the amount of those structure sizes in that measurement area. And so when we're looking at this, we see that the resolution of the human eye starts at about 0.1 millimeters, and anything under that we physically can't see. But it's important to be able to measure that, because that directly affects the distinctness of image, and we'll get into that later on. So how does the instrument actually work? So if you're familiar with the wave scan, and you've seen them before, you've seen that they have wheels on the bottom, similar to a small race car or Hot Wheels car. But to measure, you're essentially going to roll it across the surface. And so it's going to take scans as it's rolling across that surface to get an optical profile. And what you can imagine that's actually happening is there's a laser that's shining over that surface. And as it goes over each of the structures, so the peaks and the valleys, it's getting an optical profile of how that laser is being reflected back towards that sensor. And if you imagine you're scanning over a distance of 10 centimeters, and these distances are variable depending on what you're measuring. Obviously, if you're measuring something smaller, you want a smaller scanning distance, but if you're measuring a larger surface, then you want a larger scanning distance just to gather more information on that. And I have a nice little representation of what's actually happening as it's scanning. So we see the light source, the laser light source that's coming down over that sample. And as we roll it across the surface, we see that the concentration of that reflected laser source gets worse and worse as it hits the peaks of those structures. But as we go more and more into the valleys, we see that the concentration increases, and now we have the maximum amount of laser on the sensor itself, which then translates into a set of values, and you can eventually turn that into short wave and long wave through mathematical filters. And so that's essentially how a lot of our classical older models work, just utilizing the short wave and the long wave values. So with that, you can identify or objectively quantify appearance differences between two samples using that short wave and long wave. And so here we see a surface characterization using those two values. We have sample A, which looks very pleasing to the eye. It looks very smooth. There's not a lot of short wave, not a lot of long wave. And when we look at the values themselves, we see that they're fairly low. Remember, these scales are out of 100, so 0 to 100. Theoretically, if you have zero structure, you have a perfectly smooth surface, and so you're always trying to achieve zero. The problem is that depending on substrate quality, over time, as you add more and more coatings, more layers to that surface, it's going to bring out the imperfections more and more. And so what you want to do is identify how you can optimize your process to make it not come out as bad. So in this case here, we have sample A and sample B. Sample A has a shortwave of 15 and a long wave of 10. So your shortwave is already fairly low and your long wave is fairly low. And so your end result is what we see, and it's very pleasing. Whereas sample B, we have a higher shortwave, not by much, but it's only at 17. But we see that we have a very high long wave value. And so what that's telling us is there's a lot of large structures in there, but not a lot of small structures that balance it out. And so we end up with this displeasing look for sample B. So with that, we see that short wave and long wave can be pretty valuable in objectifying or showing us where these differences between samples are actually occurring. But there are shortcomings to that. And this happens because as coding systems become more advanced and they add new technology to them, you come across situations where the values may be low, but the appearance is not as good as you would hope. And the reason for that is because the short wave and long wave isn't really telling the full story of what's happening across that surface. It's only telling a small section because it's only taking specific sizes, specific structure sizes, and accounting for them. And so in this case here, we have sample C and sample D. Both of them, objectively, sample C looks slightly better, but sample D is just as bad, I would say. When you're looking at the values, you see the short wave is about 21, so it's not too high, but it's not great either. And you have a long wave of 7, so a very short or very low value in your long wave. But when you look at sample D, we see that we have both a 12 for a short wave and 12 for a long wave. So they're identical in that case. But the values are also fairly low. But the problem is that it's not telling the full story. It's only telling us that we're having 12 for short wave and 12 for long wave. And when we look at that, we see that even though they're low numbers, visually it's not a good image. And so we find that we need to further our scales or add an expanded range so that we can identify where these differences are actually occurring rather than just look at 2 values. And so to do that, instead of going from mathematical filters to just short wave and long wave, we can then increase that to cover the full structure range from 0.1 millimeters all the way to 30 millimeters. And so this essentially goes from the human visual resolution up into very large structures that you can see at about 3 meters distance. And so you can see here where short wave and long wave kind of lined up in this newer system here. But you essentially now have your WA value, which is from 0.1 to 0.3 millimeters. So very small structures. This is going to play a role in dullness. So how well that reflected image appears, if it's very sharp or if it's very dull. And the reason for that is because these microtextures are going to scatter lightness in a very different way. Then you have your WB from 0.3 to 1, your WC from 1 to 3 millimeters, your WD from 3 to 10 millimeters, and then your WE from 10 to 30 millimeters. With that, you're able to get a full structure spectrum so that you can understand where exactly each of these differences are occurring so that you can really identify what's happening and why in each coding system. And so now when we take those samples that we saw before, sample C and sample D, now you can really see where these differences are. So for example, when we're looking at the WA, which is from 0.1 to 0.3 millimeters, so very small structures, we're seeing that sample C is fairly low compared to sample D. So we have a lot less smaller structures in sample C. And then when we look at the WB value, we see that now sample C is higher in that regard. And so it has these ranges from 0.3 to 1 millimeters are a lot more prevalent in sample C. But then when we go to sample WC, which is from 1 to 3 millimeters, now we're seeing a big difference between the samples. So sample C is around, let's say, a 10, whereas sample D is around a 20. So about a 10 unit difference. And in this case, it's just enough to visually see that. So if you imagine the medium-ish structure range, when we look at sample C, it looks like it kind of blends together between the short and the long wave. But when we look at sample D, it looks very dominant in these short wave structures. And when we look at this structure spectrum, we can see that that is the case. It's very high in regards to the WA through WD, but as it gets to the WE, we see that it starts to drop down, where sample C appears to have a good balance across each of those, where you have WB is a peak there, and then you have WD as being another peak. And so with that combination, you're able to achieve a nice balance between shortwave and long wave structures. And really that's one of the main points is that if you're unable to eliminate these structures in your materials, as you add more and more layers of coatings to whatever your product is, and it brings out these defects, as you try to get rid of this, it can bring up other issues. And so the idea is, instead of trying to eliminate and get zero structure, we can create a balance of these different sizes to create a pleasing look that almost blends everything together. So jumping into DOI, or distinctness of image. I know we mentioned this in the beginning here, but this is a good representation of what that is. So we have a good distinctness of image, meaning this example here, we have very sharp outlines. We can see a reflected image very clearly. And then we have a poor distinctness of image. So now we see that in this example, the reflected image is very blurry. The lines aren't very sharp. It's not as pleasing. When we look at what DOI is and how it's where it's affected, essentially, we see that a couple different things can cause it. One being light scattering, which causes a contrast reduction, usually in smaller structures. So it looks like less than 1 millimeters. And then we also see that smaller structures can cause a distortion of the outlines. So you have two things happening there that's causing that effect. Now, how does the instrument measure this? The instrument uses a special light at 20 degrees. And so as it rolls across the surface, what it's looking for is the reflected image to reach how much is on the outside of this versus how much is on the inside, which gives you your dullness value. And so that's the calculation for it there. And like I mentioned earlier, your dullness value is what essentially gives you or starts off this DOI. How sharp is your reflected image versus how blurry is that reflected image. And what's very nice about this, the way this system works, is that it's independent of the refractive index, meaning you can take measurements on a 2K clear coat system and take measurements on a 1K clear coat system. And both of those measurements will correlate to each other because it's independent of that refractive index. Unlike a gloss meter, where if you're measuring the gloss to understand that, the refractive index is going to play a role in that. And if you find out that you're measuring a 2K clear coat system versus a 1K clear coat system, you're going to find out that the numbers aren't going to correlate because the refractive index is different. One of the other advantages is that it works on a curved surface. If you ever use gloss meters, what you'll find is that once you start to have curvature in your samples, that's going to scatter the light differently. And because of that, you're going to lose more light than what your gloss truly is. And in this case, because it's taking an account of how it's scattering, not how much light's making it to that sensor in the middle, you're able to identify what is actually going on in that system. And so with all of those values put together, with our newest addition, dullness, we're able to get that complete structure spectrum. And so now what we're covering is our dullness. So that was what we just went over for distinctness of image. But remember, that is what we can't see. So those are structures that are so small that we can't visually see them, and they play a role in how sharp or clear that reflected image is. And then from there, we have our WA through WE scales, which identify the amount and size of each of those structures in that surface that we're looking at. And here we see how that DOI value is actually made. So we see it's a combination of dullness, WA and WB, because all of those smaller structures are going to scatter light and affect how that's appeared. And so that's how we get our DOI value. And we see here for the blue line and the red line, those individual samples, which correlate to those images that we saw earlier. We have a DOI of 91 for the bottom and a DOI of 84 for the top. So getting into the instrumentation. So the wave scan is what measures these values and these surfaces. But one thing that's really important to note and really interesting is that not only is it a tool that's used to document these values and what these appearances are, but it can be also used to improve quality, not only substrate, paint materials, and the process, but it's great for troubleshooting issues and where things could be going wrong during a process. The example for this is through this little study here that was done. In this study, we have a sample here that you can see. And what was done is it was measured with the wave scan, and you can see the structure spectrum. And at each step, they were able to optimize a specific process and then take another measurement with the wave scan to see how that surface changed and how they could make it better from where it was. And so starting off with the original, we see the sample here looks very lumpy, very bumpy, very similar to the surface of an orange, I would say. And when we look at the structure spectrum, we see that from across all of the structures, it's fairly high in almost every single value. So for dullness, or less than 0.1 millimeters of surface structure, so that's what's going to affect the distinctness of image. We see that it starts off very high, so around 20. And then for your WA, it's around 40. Your WB, it's around 55, and so on. Across the board, it's very high. So what could you do in this situation? Well, one thing you could do is optimize your clear coat application. So if you apply more clear coat, and theoretically, it will fill in more of these larger long wave structures, and therefore lower your long waves. And that's exactly what happened. And so as they optimize that clear coat process, they took another measurement, and they see that now across the board, all of the structures went down in size, in number. But for the most part, the longer waves, so from your WD to your WE, or your WC to your WE, each of those structures went down drastically. But you also have a decrease in each of those values individually as well. So the next steps from there is that you can sand the primer. And so if you sand the primer, this is how that affects the coating or the surface there. So we go from a lot of short waves, because we're very short wave dominant in this case, to now when we sand the primer, all of those short waves go down, and now we're back at being long wave dominant. But for the most part, we still see a decrease in all of the structures, which is good, because we want to remember, ideally we want 0 for everything. But if that's hard to achieve, we can simulate a perfect appearance by having a balance between short wave and long wave. And so after you sand that primer, we have, again, very low values across the board, but it's still not perfect. And so what can we do now? We can optimize the primer or the top coat. And now what we see is that this brings up the short wave just enough. And really what you're looking for is about a 2-to-1 ratio, where you have a little bit more short wave than long wave, but you still have a balance here. And so now when we look at it after optimizing the primer and the top coat application, we see that it brought the short wave up. And so this brings in a good balance of short wave and long wave. And so bringing each of those steps together, we can see how we started from a surface that had lots of waves and looked very orange peely. We went from there all the way down to this last step here, which has a structure spectrum of about a 2-to-1 ratio. And we see this is the best look that we could achieve in this case. So getting into one of the scales, so we talked about short wave, long wave, the dullness, the DOI, and then the WA through the WE values. But another one that's used in a lot of manufacturing is the R scale, or the rating scale. And this is made up of pre-existing physical samples. And so the scale goes from 1 to 10. And when you're looking at it, you can set different tolerancing in the instrument as well. So for example, this is a tolerance system based off of premium and non-premium vehicles. And so if you have a non-premium vehicle, you can set it up to have a minimum of 8.5 for your R value. And so you need to achieve that. And that'll appear as green on the wave scan itself. So that'll appear as passing. And then let's say you have another tolerance for anything that's below an 8.5. So let's say you want to do an 8.0 to 8.5, and that'll come up as yellow. And so it almost gives you a warning that something's going wrong with your system, whether it be in your clear coat or your primer or your substrate. It's essentially a warning system telling you that, hey, there's something happening within the process that's affecting the results here, that could be leading to things coming out of tolerance. And at that point, you could stop, take a look at the process, and figure out where the issue is happening. And then obviously for horizontal and vertical surfaces, those tolerances would be different. And that's just due to gravity and how it affects coated surfaces. We have a lot of sagging sometimes, and so you want to have different sets of tolerancing for whether it's a horizontal surface that's going to be sitting flat in an oven versus a vertical surface that could experience some type of sagging as it's going through the oven. And then lastly, this kind of just goes over everything that the instrument has and kind of the major points here. So we have the structure spectrum. And if we look at the first half of this structure spectrum again with the DU value, so less than 0.1 on the structure spectrum, and then we're looking at WA and WB, we see that those are mostly made up into what we call the DOI value. And then the R is a function of the short wave and the long wave coming together. And so those original classical scales, the short wave and the long wave, can come together to create that R scale, which is what we saw earlier with different tolerancing set up. And we usually see issues in the DOI resulting from substrate or primer. And then the top coat usually influences the R value or the longer waves in that situation. From there, that's essentially it. So now we'll open it up to questions, and I'll give it back to you, Sherry.
Very much for that, Noah. Sorry, I was trying to get in the chat for someone that was leaving our YouTube channel, and it just the coffee didn't seem to want to work correctly. But it's YouTube at Bic Gardner USA. You will get, and well, I'm sorry, let me take a step back. So youtube.com/at Bic Gardner USA. And then all of the webinars are under this web seminar archives. If you need to access that then. Yes, we can also send a certificate for the course. I'm not sure. I think the system may say something about it sending you one, but the link doesn't always work. So we can send that to you. Not a problem. Do we have any questions about the topic that Noah discussed or anything right now? Oh, I do see one here. Noah, what is the most significant number to use for optimizing your coding for appearance?
Great question. So over the years, there's been many scales that were developed. And we actually have some good resources on our website, Bic-Instruments, where we go into what those scales are, how they were made, and what they're used for. But for the most part, I would say if you really want to get a good understanding of what's going on with your system and how to really make it better or optimize it, is really to use the scale from DU to WE. And the reason this is the full structure spectrum, there's a better picture of it. So your dullness, like I mentioned before, that really is what affects your DOI, your distinctness of image. But each of these values really identify what's happening with the surface. And it's nice to have one scale that you can go off of and say whether something passes or fails. But the problem with that is like I showed you in that one case, where if you're just using two scales, even if you're just using two scales, in some cases, it'll tell you if you pass or fail, but it's not giving you a full understanding of the story. And so you can have cases where the numbers might make sense, but it's not telling you the full story. And therefore, if you truly looked at the surface, you would see that it's not really matching up with what the numerical values say. And in that case, I would suggest using the entire structure spectrum to really understand the full picture of what's happening. Because in the end, there's a lot of variables that are at play when we're looking at something and judging the appearance of. So it's best to have a lot of data to look at in order to correlate the two.
Thank you, Noah. We do have a question. How would you recommend measuring surfaces with orange peel when the dullness is below the WaveScan's range?
Yes, great question too. So for those of you that are very familiar with the WaveScan, it works for high gloss surfaces and some semi-gloss surfaces, but when you get into the matte surfaces, there's not enough data that gets reflected back to the sensor to give an accurate representation of the values. In that case, there is a setting that you can use on some of the WaveScan models, and it's called plausibility. If you turn that off, what that does is it's important because it no longer correlates data. And so what that means is you can't, when you turn that off, you can't necessarily take it and compare it to other data that you've collected in the past, but you can get an understanding of where that material is as far as appearance goes when that surface is way too dull to measure normally. And so if you turn this plausibility off, they're able to measure and get values of that surface that's very dull. In some cases, if it's really dull, you're not going to be able to measure it just because it won't get enough information. But you can get it down to, I believe it's a dullness of 40, which is fairly low. And you can get values off of that. But again, you can't use that to compare to other data just because it's not collecting it in the same exact way. If that makes sense.
And Aaron, if you have more questions about that, we can certainly put you in touch with Noah. Any of our emails that you send, you're always welcome to ask a question back from any email you receive from us. And we will certainly, typically they come to me, and I will put you in touch with the best person to answer that question for you. We also have Noah. Could you please explain the difference between DOI and dullness one more time?
Yes, I think I've used them interchangeably a couple of times, which was my mistake. Dullness is really what you see on this screen here. Dullness is just the value that's measuring structures less than 0.1 millimeters in size. The dullness can then be taken into a value. Let me pull this up here. The dullness is taken into account with the WA and WB to give you your DOI value. So if you think of dullness, it's just very small microtextures. And as you know, if you've seen a matte surface and a glossy surface, microtexture is what makes that matte surface because it scatters light differently than a glossy surface would. And so the dullness is really just small structures that it's measuring, whereas the DOI is a combination of several values to give you an understanding of how well or how clear the reflected image is. If you think a mirror would have a perfect DOI, like I would say 100 DOI, because you have a perfectly reflected image, whereas let's say a matte black surface that doesn't reflect very well would have a 0 DOI because it's not giving you a clear reflection of your face if you're looking at it.
Thank you. There's another question. Does the measurement direction affect your readings?
Yes and no. It doesn't necessarily. Yeah, it doesn't necessarily affect it. I mean, there's definitely certain cases where the structure in your material is direction dependent. In that case, it would affect the orientation would affect your results. But for the most part, this phenomenon of orange peel is not really direction dependent, and therefore I would say it doesn't always matter the direction unless you see a clear example in your material where it's direction dependent. I don't think your data would be affected if you took it differently.
Excuse me. Good. Are there any other questions from the attendees at this time? Noah, is there anything else that you would like to add?
I would add that my email is up here on this last slide here. If anybody has any further questions that we can't get to today, just feel free to email me. We can have our own one-on-one discussion or just conversation over email. Feel free to send any samples my way if you ever want to get an understanding of how this instrument can be applied to your process or your materials. It's a service that we offer, so feel free to reach out.
And it looks like our next webinar for anybody that's interested is on dispersion, and that is next Tuesday. And then we do have our office in Europe is also doing a webinar on hardness and flexibility on the 19th. And then we obviously move into March. So if you ever have any suggestions or anything that you would like us to cover, please feel free to, send us a message and we'll get a webinar together for you on that. Oh, I think someone is typing, so we'll pause for just a moment. Oh, and thank you. Well, thank you for attending. Thank you for taking your time out of your day and spending a little bit of time with us. And we look forward to having you at our future webinars. Thank you.